Okay, let me start refreshing something and then I will start later on. Okay. So, to recap, yesterday last week what we did, we studied this problem of dynamic connectivity where we are given a set of nodes V and this set of nodes is fixed, it is not changing. On the other hand, we have a set of edges this is changing. And we want to maintain the connectivity information. So, we want a data structure that will support two updates. So, insert this edge UV into the graph or delete this edge. UV from the graph, and the data structure should also support the following query. The query is, you are given two nodes U and V, tell me if they are connected or not, that is whether they belong to the same component or not, same connected component or not. So, last week what I tried to do was to give a very high level overview into what was going on in this data structure. Today I will try to be a lot more systematic and give you the complete algorithm as well as introduce the dynamic tree data structure which will be used as a subroutine here. And I also intend to present two different dynamic tree data structures, one is called ET tree and the other one is called top tree, but I do not think I will be able to cover both of these today. So, maybe one of these data structures will be presented tomorrow, next class. Okay, so this was the goal, and we observed that there is this thing called the dynamic tree data structure. What does it do? It just solves this problem only when this set of edges is acyclic. So, V is the node set as before, and you can say F is a acyclic set of edges and the updates are the same as before. Insert UV, delete UV and query. The same query. Now, we are just given the guarantee that the underlying graph is a forest. The thing is that with dynamic tree data structure, we can actually answer a lot more queries, and this will be needed in the dynamic connectivity algorithm as well. So, let us recall the very high level intuition of the dynamic connectivity algorithm. What was it? That we are maintaining a spanning forest of the graph to answer these connectivity queries, and say this is the spanning forest that we are maintaining, and there are some non tree edges. So, there might be different connected components of course. and there are some non-tree edges. So, these are the non-tree edges. Okay. And now recall that if a non-tree edge gets deleted, this is the easy case because we do not need to change our spanning forest. The hard case was when a tree edge gets deleted. So, suppose this tree edge gets deleted, then we need to find what is called a replacement edge for it, meaning that okay, this tree now gets split into two halves and we need to find if there is an edge that crosses this cut, that is the replacement edge. Okay. And recall that again from the last class we said that the high level idea was we will go to the smaller half of the tree and probe all the non-tree edges incident on this half and check if any of them is a replacement edge, and that was the high level idea. And why does this help? Because if we fail to find a replacement edge, we have done a lot of computation. However, the size of this connected component is getting halved. So, we probed this non-tree edge, we failed, but the size of the connected component it belonged to gets halved, and this cannot happen more than log n times. Okay. So, now as I said, today I will be a little bit more formal and systematic. Yes, last week I was being hand wavy saying that oh, you can maintain these trees using the dynamic tree data structure. So, now today let us try to formalize what updates and what queries should our dynamic tree data structure support, so that we can carry out this action plan. Okay. One thing is of course, it should support these updates and queries, right. This is how we are just updating these subtrees. Now, I claim it should support some more updates and queries. Can anyone point out one, say query, let us say query. Exactly, exactly. When this tree edge is getting deleted, we need to quickly find out which half is the smaller one, right, and we need to find that out quickly. So, our dynamic tree data structure should support this query, that size of V. What does this mean? Look at the tree containing V, what is the number of nodes in that tree? This is one thing, clear? Otherwise, we cannot execute this. What else do we need? Any other suggestion? Exactly. How are we going to detect these non-tree edges? Okay. Now, let us ask ourselves again, what exactly do we need? In constant or log n time, we should be able to find a node in a subtree that has at least one non-tree edge incident to it. So, we will say that okay, here is the subtree, tell me if there is any non-tree edge incident to it at all. If yes, just give me a node where I could go to, and then we can of course find that non-tree edge by looking at the adjacency list, right. I mean, that is not going to be a trouble.
So, we are not allowed time proportional to the size of the subtree?
No, of course not. We need to do this thing in constant or log n times time. Okay, we need to do this quickly. So, I am going to phrase this in a slightly more abstract way. So, in this dynamic tree data structure, we will have one other thing. That thing will be called labels. So, L is the set of labels. So, you can think of a label as a non-tree edge here, and each label is assigned to one node. Okay. So, there is a function f that says given any level which node it maps to. So, you can think of it as follows, say this is u, this is v, you have a non-tree edge u v, we are going to create two distinct labels for it. So, this is one level and this is another level. So, we are going to assign this label to u and this label to v. Okay. So, we have a set of labels, each label is assigned to a node, and then of course, we need to support some more updates. Which one is it? Create a label, create label L, assign it to node V, and of course, delete label. So, the way we will store this label is this set of labels will be stored as a doubly linked list, and for each entry in this list there will be a pointer that points to the node that is assigned to it. Okay. But each node V can get multiple labels, okay, because each node V can have many non-tree edges associated with it. And we need to answer this query, right? What is the query? Sorry? Okay, you just need to store this set of labels somewhere, right? There should be one entry for each label, and from that entry there should be a pointer to the node where it was assigned to. You can store that set, okay? Okay, doubly linked is not.
So when you create a label, right? So you say create label L comma V. So a label always corresponds to a non-edge?
No. In this context, it corresponds to a non-edge. But I am going to define what sort of operations this dynamic tree data structure supports, right? In some other context, the label can mean something else, we do not know. Okay. So, the point is that I am going to first finish describing this algorithm, assuming this data structure, and then I will go on to describe this data structure, how to implement this. Okay. And what will be the query? The query is going to be something like this, say find label V. What it does? It says look at the subtree containing V, first tell me if there is any label assigned to that subtree. If no, we are fine, otherwise just return a node which has at least one label assigned to it and which belongs to this subtree. Clear? This is what we want here. Any question? Yes.
U comma V comma U is one label. U comma V comma V is another label.
Yes.
One needs to relate it again. From one we want to go to the other label. Then we next adjacent in the linked list or something like that.
No, I mean they should be consistent in the sense, right? I mean, why are we creating two labels? Because we do not know, we might have to probe this edge from this subtree or this subtree, we do not know which, right? So, there should be two labels and they should be consistent in the sense that if this non-tree edge gets deleted, we should be able to delete these two labels simultaneously. So, you can figure out how this will work, right? I mean, each edge in the graph will have pointers to these two labels, okay? So that we can ensure that either both these labels are present or none of them are present.
So your tree is given in some format, adjacency list or whatever, and you have this pointer to this doubly linked list for this. How is your tree given?
Oh, this tree? That
yeah, the dynamic tree data structure.
Oh, that is what we are going to consider later on. Right now, we just assume this as a black box. It's going to represent the tree in some form. We do not know what. Okay.
And all your running times are logged in.
Yes. Now I am going to come to that. Exactly. Yes.
So find label B is not give me a label associated with vertex B.
No.
It is with the subtree
Containing V.
in any node in the subtree containing.
Yes. okay, because this is what we are doing here, right. I mean, this edge gets deleted, we are just looking at this node, asking, look at this subtree, is there any non-tree edge incident on this subtree? Now, the run times, we are going to later on, we are going to give a data structure which supports each of these operations in log n time, log n worst case time, and note that n is the number of nodes, m is the number of edges, and also all these operations in log n time. Okay. Okay. Now, we move ahead with the description of the algorithm.
In particular, you do not need a map from labels to which edge it corresponds to. You just go to that node and just look at its adjacency list. So here we have a kind of bijection between, not a bijection, some function between the non-tree edges and the labels, right? Every
Yes.
non-tree edge corresponds to two labels.
Yes. Okay.
But we don't need a reverse map because we just go to that node and look at its adjacency list.
No. Okay. Let me try to get your question correctly.
So,
You are saying, why do we need this map?
so that map is, I mean, so you go to B,
Hmm?
you ask for a node which has a label, so let that node be U. So we know that U has some non-tree edges. That is all we want. So then we look at the adjacency list of U and look at the edges which go.
Yes.
And then,
Yes. Okay.
So that takes more time, that's okay.
yeah. Then,
Because you're going to scan that as a list of you, right?
Okay. You know what? Okay.
That's
Le-
very precise.
No, that will not be amortized. Okay. Maybe this is the answer to your question. Recall that we are going to partition these non-tree edges, I mean all the edges in the graph in layers, right. So, if you go to V's adjacency list, you have to look for the replacement edge at a particular layer. So, that is why you need this map and also this reverse map. So, basically in this data structure, how it is stored is, from each label you have a pointer to the node it is assigned to, and from each node you have pointers to all the levels associated with it. Okay. And the purpose of this thing is that you never know whether a particular node V has any level associated with it or not. You cannot afford to probe all these nodes, that will take much time. Okay. Okay. So, let us go ahead with the algorithm. This is for the dynamic connectivity. Okay. What was the algorithm? First, each edge, I mean we will partition the graph into log n layers. So, I am calling this thing layer here and this is label, so that we do not get confused. So, this is basically the layer of edge E. Then EI is the set of all edges lying at layer I or below. Okay. And GI is the graph induced by these edges. This is from last class. So, what we have? We have this, right, that E0 is contained in E1, this is contained in E2, E log n. This is clear, right. Now, we are going to maintain two invariants. Invariant 1, every component, connected component in GI has at most 2 to the power I nodes. So, in G log n this is trivially true, because in this graph every connected component has at most n nodes. Now, in each of these subgraphs E0 to E log n, we will build a spanning forest. So, Fi is a spanning forest in GI, and our second invariant is that these spanning forests are contained like this, just the same as this edges, edge sets. Okay.
Just a question here. Does the new definition of forest isolated vertices at all?
Yes. So, spanning, by spanning forest I just mean a set of edges. So, if there are isolated vertices, of course, no edge will go inside. I mean, this is just a set of edge. Okay.
So F0 is just cache vertices.
Yes, F0 is empty or whatever, F0 or F1. I mean, this is just a boundary condition. You can figure it out what will happen. Okay. Now, let us first quickly go through invariant 2. What does this mean? One interpretation is that we are just building this forest incrementally. How will you satisfy invariant 2? In the static setting, forget about dynamic running time or whatever. What will you do? You will first look at this graph in E0, find a spanning forest, that is it. Okay. So, you will build this spanning forest like this. So, F0 will be a spanning forest in E0. Then you look at these edges. Look at the edges in E1 that are not part of E0 and try to add as many of those edges as possible to F0 without creating a cycle. Okay. From that you will get the edges in F1 minus F0. This is how it is going on, and then you iterate. In other words, you can say that if you look at it's just like running, say, Prim's or Kruskal's algorithm on this entire graph G, where the layers of the edges are their weights and you want to find minimum weight spanning tree. How will you proceed? You will first look at all the edges with weight 0, layer 0, find a spanning forest. Then look at all the edges of weight 1, layer 1, augment that forest. This is how you get F1, then you go to F2 and so on. Is this part clear? Because if you do not have this picture in mind, it will be very difficult. So, let me just illustrate this by one other picture. Look at forest I, right? And say these are the connected components, okay? Ci1, Ci2 is here, then here is Ci3, say this is the forest Fi. From Fi, how will you go to Fi plus 1? You will just look at the edges of layer I plus 1 and all the edges that are like this within a component, you do not do anything. If you find an edge E with layer I plus 1 that joins these two components, you just merge them in Fi plus 1. Okay. So, this is one other such edge. So, you merge this component, probably you find this edge, you merge this component. So, in Fi plus 1, so when you are going from Fi to Fi plus 1, you will see that these were the components in Fi, and in Fi plus 1 you will get the super components. So, couple of components from Fi got merged. So, these are the components in Fi plus 1, and you go up. Okay. Any question?
So you starting with E log n layer, right?
No, you are starting from E0.
We're starting with all the edges. Are we starting with the empty graph? Or we starting
No.
with all the edges and then delete?
Okay, I think the confusion is here. One is in the dynamic data structure, are we starting with an empty graph?
Last time we said we start with all levels L and then the next thing we had L minus 1 thing. So I thought maybe you're starting with log n thing and then.
Okay, so last week what I tried to do was give a very hand wavy explanation. Right now what I am saying is, suppose these layers has been assigned to the edges, and suppose invariant 1 is already satisfied. Just in the static setting, how are we going to build this forest so that invariant 2 is satisfied? Okay. Is that clear? And this is how we are going to build it, and this forest will look like this. That is another point. If you take a snapshot of the data structure at any intermediate step, I mean the picture will be like this, what is going on. Any question? Now, okay, so let me erase this part.
I understand that this implies this constraint.
Yes.
The static
Yes.
expansion implies this static. But suppose Vi.
Okay, you are saying does this imply this?
So I just have one doubt. So if Vi plus 1 minus Vi has edges from Ei and not just Ei plus 1. If we have the constraint, then Vi plus 1 minus Vi has only edges from Ei plus 1 minus Ei. Then I think this will go.
There is no VI at all.
Ei.
No, that is by definition, right?
No. Fi plus 1, sorry, Fi plus 1 minus Fi. It can have edges from Ei and not just Ei plus 1 minus Ei.
Okay, yes, I agree. I do not claim that this implies this. I am not claiming this. I am just saying that, okay, this is what the algorithm is going to maintain, and this implies that invariant 2 is always satisfied. Okay. Now, the algorithm, the detailed algorithm, just keep this picture in mind and these invariants. First, okay, first let us just answer the query, right? How will you answer the query? That whether any two nodes U and V are connected or not. You just look into f log n and you just check if they are connected in f log n or not, and you will maintain a dynamic tree data structure on each of these forests. We will come to the detail later on. Okay. So, the query time will be order of log n. Okay. Just look at f log n, that is the answer. Now, insert. So, an edge UV got inserted. First, we need to assign a layer to it. Anyone? What should be the layer? What is the laziest thing we could do without violating any of the invariants? Right? Assign the layer to be log n. So, edge UV got inserted, its layer is, just set the layer to be log n, then check, I am just going to write check f log n. By this, what I mean is as follows: see if you insert LUV into f log n, does it merges two component or not? If yes, merge the two components, right. So, suppose f log n looks like, so this is f log n suppose. Just check if you add this to edge UV, it merges these two components, and this you can do by looking at the dynamic tree data structure for f log n. Okay. Now, there are two options, right. One option is that you found that this edge UV was like this, it was in between the same component, you do nothing. Otherwise, you found that okay, this connects two components, just make this thing part of f log n, you stop. Does any of these two invariants get violated?
So is there dynamic tree has a sum operation to merge two things?
Yes. So,
Insert.
insert, right?
Will
Yes, yes.
So we are not updating E log n.
Yes, we are updating E log n. So, for the time being, you can just think of this as follows, forget about these labels things for dynamic trees, just for the time being, okay. F log n is a dynamic tree on E log n. Oh, sorry, no, I take it back, When I say that set the layer of UV to be log n, this implies that you insert it into E log n, okay. And then you probe the dynamic tree data structure f log n.
So is your data structure just dynamic tree for each of the log n forest or log n plus forest?
Yes,
You also need something with a non-tree edge.
yes, that will be the labels, and I will come to that later on.
That you have to do now, right? Because if this new edge you added is a non-tree edge,
Yes,
for each log n,
yes,
you
and
need to do something.
yes,
Maybe that sort of
yes. Does that answer your question? Okay. And now, yes. So if this, you see that this is a non-tree edge in f log n, then you create these two labels which we discussed previously and insert that into the dynamic tree data structure. Okay, and everything can be done in log n time.
So what you do is you get a new edge, you first add it to E log n, you try to insert it to F log n.
Yes.
If that doesn't work, then you create new labels and
Yes. Okay. And why is it okay? It's okay because first of all, note that nothing is changing in this part from E0 to E log n minus 1. It's exactly the same as it was before. So, of course, invariant 1 and invariant 2 are true till layer log n minus 1, no question, right. And in layer log n, I mean, what is the matter? I mean, in invariant 1 just said that every connected component has at most n nodes. So, this is also true, and this you are making it true by the last thing by doing this here. Okay, so is insert clear? What is going on? So, the point is that the insert takes log n times.
So updating the label thing is not clear, but you're going to come to it later.
Okay, what I am going to do later on is
You
to
have said, for example, how you are representing the non-tree edges. Right? Or what is your data structure other than the dynamic tree for each of the forests?
Yes, I am going to come to that later on, because it is better not to go into that right now, because delete is a bit more involved. Let us first cover delete. Okay. So, insert is clear. Now, delete. And what does it mean? It means that insert is worst case log n time, there is no amortization. It is the delete where we will use amortization. Now, let us just assume that the level of UV was k. Okay. So, this is Ek, E log n, and also note F0 So, the layer of this edge is k. What does this mean? That this part remains completely unchanged. We do not need to worry about this at all. Is that clear? Are you following it? We only need to start at layer k. Okay? Yes? So, we only need to fix this part. That is what I am claiming. So, the first step is obvious. I mean, just delete this edge from Ek to E log n. That is clear. And now, there are going to be two cases. Case 1, depending on whether this edge UV belongs to Fk or not. The case 1 is the easy case actually. So, suppose UV does not belong to Fk.
That means UV is a label, not an edge.
Yes. And then you can see that you can just keep this forest intact. Can you see why? I mean, you just need to delete this edge from these subgraphs, I mean Ek to E log n.
You also delete the two labels that are.
Yes.
Actually, don't know beauty about labels.
Let us not go into that, because I am going to go into that a little bit later. Okay. Okay. So, case 2 is the more interesting part. Where UV belongs to Fk. Now, UV belongs to Fk means UV belongs to Fk till F log n. So, we first have to delete this edge from Fk to F log n. Yes.
So when you said that, suppose UV was not an actual edge in Fk, so it means it's not an edge in any of the trees.
Exactly.
Any of the forests. The second thing is then, is it a label in every one of these forests or just in Fk?
Okay, so I think it will be easier if you do it like this. Right now, just look at the combinatorial structure as to what is happening, ignoring how it will be implemented in the data structure level. Just try to see combinatorially what the algorithm is doing. Once we are done with that, we will go into the representation in the data structure, because it is easier this way. Do not confuse these two. One is the actual action the algorithm is taking on these structures. The other one is how is it being represented in the data structure. Okay? So, right now we are at the higher level. Just see what the algorithm is doing on these edge sets. Okay? but you mentioned one crucial property in case 1, if this edge does not belong to forest k, then it does not belong to forest k plus 1, k plus 2 and so on, right. This is because of this incremental property. So, this is easy, this is hard. So, first of course, suppose we have adjusted these edge sets E k to E log n, meaning we deleted u v and then we deleted u v from f k to f log n. So, basically this is saying, again at looking at the higher level, do not go into the data structure detail right now. For I equal to k to log n, sorry, this just says delete u v from E I and F I. Okay. Now, at this point, after we have done this, is invariant 1 satisfied? First question. It is satisfied, right? Can you see this? Because it was satisfied earlier, now it can only decrease, and this invariant 1 does not depend on this forest. Okay. Invariant 2 might fail. Why it might fail? Because f k may not be a spanning forest of E k anymore, and f k plus 1 need not be a spanning forest of E k plus 1 anymore. So, invariant 2 might fail in this entire range, we do not know where. Okay. So, we need to fix invariant 2. Okay. Now, what can we do? Okay. Let me erase this part. So, how are we going to now fix invariant 2? Again, forget about the running time, forget about the data structure, just look at it combinatorially. How will you go ahead fixing this? What is the naive approach just to fix this? Okay, first question, let me draw this thing again here, because this is a very nice figure. So, this is E k, so this is E log n. F k okay. We start by asking, is f k a spanning forest of E k? If yes, we go to f k plus 1, ask the same question. If yes, we go to f k plus 2, ask the same question. At some point in time, in the worst case, if everything is okay, f log n will be a spanning forest of E log n and we are done, nothing to change. But the interesting case is somewhere here, f I is no longer a spanning forest of E I. Okay, this is where we get stuck. Now, can you check that if this is the true, if this invariant 2 fails here, it will fail with f I plus 1 as well, f I plus 2 as well, and f log n plus as well, right, because of this containment property. So, it just failed everywhere from I to log n. Okay. How are we going to fix this? So, just look at this forest f I. Say this was the edge u v. So, this is u, this is v, this is f I. I am just drawing f I. Okay. And these were the connected components of f I. And this guy had level k. So, k is less than f I. Okay. You deleted this edge. But Fi is no longer a spanning forest of Ei means, what does it mean? That there is a replacement edge that connects these two components, right? What will be the layer of such a replacement edge? Exactly I. It has to be I. It cannot be less than I. It cannot be I plus 1, right? Why it cannot be less than I? Why it cannot be I minus 1? Because if it was the case, the invariant would have been violated at I minus 1, right? The same thing just happens, right? There is a replacement edge with layer k, yes, layer k.
See, the invariant fails when that edge that it created was a cut edge. So if it may not be a cut edge for all these blocks, but then beyond, if it is a cut edge for all these blocks, then beyond that it's not.
Okay. So in Fi there is some replacement edge like this, and this guy has level I, layer I. Okay. Suppose you found that edge somehow, again ignore data structures, ignore algorithms, suppose you just found that edge, and suppose I now say that just insert I into Fi, then it is fixed, right? Fi is now a spanning forest of Ei, no question.
Why was it earlier not a spanning forest? I mean, you're not looking for a spanning forest that minimizes the number of components.
Yes. No, we are just assuming the situation where for some I in this range, this invariant violates for the first time.
Yeah, I mean, why would it happen when Fi is not a spanning forest of Ei?
Why would it happen that Fi is not a spanning forest of E?
What is, in what condition? Because all we've done is we've removed an edge UV from Fi, right?
Yes.
And that edge was already was also removed from Ei, right?
Yes.
So I mean,
No, but Ei contains a replacement edge. Ei minus 1 does not.
No, I think that's the point is, all isolated vertices, for example, is also a spanning forest of any.
I mean, are you looking at spanning
Maybe
forest
this
which
one.
minimizes the number of components?
Yes, yes, okay. Okay, so that's a very silly mistake. Throughout the lecture, when I talk about spanning forest, it's a maximal spanning forest. Okay? It's unwritten rule. I am not talking about sub-maximal spanning forest. Okay. So now I say that just add this edge xy to Fi. Then Fi is now a spanning forest of Ei, right? Clear? Now I say just add this edge from Fi to F log n, okay? Do this for everything, because this containment relation must hold, right? So basically what you are saying is that for all j greater than or equal to I, just make Fj to be the union of this. Then can you see that everything is fixed now? Because if you do not see that, because the components are being split, right? I mean, as you go down. So if you fix something at a lower level, that fix carries over to the higher levels. Okay? So first he will do this, and then in case 2, the last thing will be for I equal to k2 log n. Okay, I don't think I will be able to finish this. Okay. Try to find a replacement edge for UV at layer I, okay, and if you succeed, then stop. If success, I am just going to write it like this, okay. Then you just stop. After adding that edge, from layer I to layer log n. This is the algorithm. Now we are going to analyze the running time.
If there is no replacement,
I mean, you fail every time, then you just finish. You have not made any changes. You just say that okay, both the invariants are now satisfied, right? Okay. Now, first question before we go forward, in this scheme, where did we use invariant 1? We did not, right? We just looked at them independently. We say that okay, this is how we will fix invariant 2.
We did, right? Because the edge which you deleted, when you were fixing this, right? I mean, the reason why it got because you were maintaining that invariant before with this particular edge, and that replacement edge which you found between these components, right? Whose size together was something, right? Which was maintained at every state after that.
Okay, so the point is that what he was suggesting, I think, is earlier the size of these two things together was at most 2 to the power I by invariant 1, and now we found this replacement is the size remains 2 to the power I, and this is true at the higher level as well. The size is at most 2 to the power j at each level or layer j.
So how do you find out if Fi is a spanning forest?
That's what we are going to do now, right?
So you have done it.
Yes, I just looked at the abstract algorithm, what it will do. Okay. Now, still at the abstract level, we will go to the data structure question later on. We are going to run something a little bit more sophisticated. We will stick with this framework, but to bring the running time down, we will do the following. This is what we discussed last week. Now, we are going to discuss it in a little bit more detail. Let us look at this Fi. Okay. Let us just illustrate this. This is U, this is V. This level at the level here is K. And now we are just trying to find replacement edges of this form. Okay. The first point is that the total size of this component is at most 2 to the power k. So, let this total this tree let it be T, and this part I will call it Tu, and this part I will call Tv. Fi. Oh, sorry, 2 to the power I. Did I say 2 to the power k? Sorry, mistake. So, suppose I am just looking at a generic iteration of this for loop or what is going on. We have fixed everything till Fi minus 1. Now, we are looking at Fi. Okay. So, the size of this tree by invariant 1, the size of this component is at most 2 to the power I. Let us say that Tu is the smaller one. We will go to Tu. So, the size of this guy is at most 2 to the power I minus 1. Okay. Now, it just means this, that it does not hurt us if we look at all the tree edges in Tu and push their labels down to I minus 1. So, how does Tu look like? Tu contains labels. So, the level of an edge in Tu varies from 0 to I, right? Tu, the tree edges in Tu, their labels are in this range. What we can easily do is just look at all the tree edges in Tu with label I. So, for all tree edges in Tu with L equal to I, we can just set L to be I minus 1, right?
the ith.
Yes. Since we know that there is no replacement edge below the ith level, I mean, what will happen? I mean, this will just become a component at level I minus 1. Earlier, probably it was not a component. But we are fine with this, right? It still satisfies invariant 1.
And you don't want to do anything with the non-tree.
Yes. Now, that is the next part. First, we will do this. Then we will look at all the non-tree edges incident to TU here, probe them one after another. Whenever we find a replacement edge, suppose we are probing an edge xy and we see that this is a replacement edge, then we will do this fix, whatever we discussed earlier. Otherwise, we find that this edge, say xy is here within this component, we can just decrement its level again to I minus 1, right? And this is what we will do. So, the thing is that each time we are probing a non-tree edge, either of two things happen. One, we have found the replacement edge, then we are happy. Otherwise, we have decreased its level by 1.
Can you only look at tree edges, non-tree edges in this particular
Yes, in this particular level. Now, I am just going to write this thing down. I am just going to describe this thing for I equal to in so TU is the tree in Fi containing U, and TV is the same thing containing V. We know that TU is less than TV, suppose, and this implies that the size of TU is less than 2 to the power I minus 1. Okay. So, what are we going to do? We are just going to say and of course, this means that adjust the forest I minus 1, right? You have to insert that edge into that forest. So, this is what you do for the tree edges, and then edge with respect to here means incident to TU, right? So, at least one of its endpoint is in TU. At layer. So, this just means look at all the non-tree edges in TU at layer I. If E is not a replacement edge, then you decrease its layer okay, decrease its layer to I minus 1. Otherwise, add that edge to f log n and then return. Can you see this part of the board, last line? Okay, any question about the algorithm? Now we are going to look at the data structure. Okay. How will the runtime analysis go? Recall that insert takes log n time. We are going to say that delete on average takes log square n time. This is how it will go. Okay. And the idea is as follows. Look at step A. This, using the dynamic tree data structure, we will show how that this step can be performed in log n time. I mean, just identify the node, the tree that is of lesser size, and then here what we need for this step, we need to quickly identify the tree edges at layer I. We cannot afford to visit all the tree edges in TU. Okay? The tree edges in TU whose layers are between 0 to I minus 1, we have to skip them completely. We just need to visit the edges of layer I, and then we are just decrementing their levels. Okay? And here what are we doing? Again, we are just finding the non-tree edges at layer I, then either we are decrementing its level or we are just adding it to the forest from fi to f log n, and this just creates a fix and we just stop the procedure. So, basically, can you see that each time we are accessing an edge, whether it is a tree edge or a non-tree edge, we are decrementing its level or we are stopping. So, when are we accessing an edge? We are accessing a tree edge here. This is a point where we are accessing a tree edge. This is a point we are accessing a non-tree edge. In both these two steps, we are decrementing its level. And in this step, we are also accessing a non-tree edge. However, we are just stopping. We are not doing anything else after that. Okay? So, this step, add this edge to the forest from fi to f log n. How much time is it going to take? You do not have to even think about the details. Log square n, right? Because there are at most log n forests and you are inserting them. So, this is log, and each insert takes log n. So, this step is going to take log square n in the worst case. This is the worst case time. So, when you are analyzing delete, you will say that okay, in the worst case it takes this log square n time, and these costs we are going to amortize because it is performing a lot of these operations, but each time it is deleting the level of the edge, and this cannot go on for log n times for every edge. Now, is it clear at this level of abstraction? Now, we are going to go into how to represent the dynamic trees.
Before we go there, so you said that okay, I take this edge. So in the second step, right? Step B. So I pick out an edge of label I, I reduce it level, basically, and then I push it into fi minus 1. So doing that will, so pushing it into fi minus 1 will take log n time, right?
Yes.
And the level goes down log n times. So
Yes. So,
so overall again, aren't you?
it is log square n again, right, per edge. So, here you decrementing this thing and adjusting fi. So, this costs log n. What is going on here? E is not a replacement edge, you are decrementing this, and as we will see that we have to adjust the dynamic tree data structure. I mean, the labels there will change.
Every edge you're paying
Log square n, yes. Okay, clear? Now, how are we going to represent this thing as dynamic tree? So, the thing is that these are the details, but to my mind the one level summary is this, that the size of the connected components are getting halved. That is the one level intuition. Then this is just working out the gory details. Okay. So, what will be the dynamic tree data structure? The dynamic tree data structure will be for each of these layers to log n, maintain the forest Fi as a dynamic tree. This much is clear, right? And you can see that this takes care of this operation and this operation. Okay? However, this does not take care of how are we going to identify the tree edges of level I, of layer I, and the non-tree edges of layer I, right? Because we cannot afford to iterate through all the tree edges. For this part, how are we going to do that? Oh, it is the data structure that we described before, the abstract data structure. Yes. Yes. So, we are just going to invoke that data structure while maintaining this thing. Okay. Okay. So, how are we going to find the tree edges at layer I? We are just going to treat them as labels. So, for this dynamic tree, we are just going to create two sets of labels. This is the tree edges. At layer I, and say this non-tree. This is the non-tree edges at layer I. And we know how these labels will be associated, right? I mean, look at any edge that is treated as a label, it will be associated with both of its endpoints. So, now when we are doing this, for every tree edge this, what are you going to do? If you just recall what we described, we are just going to say that, okay, find label Li tree, I mean with respect to this set of labels. Just give me a node which has one tree edge incident to it of layer I. And then from that node we can just go to the back pointer and find that edge. So, this we can just report these edges in log n times per edge. Okay? And similarly here. Any question? Oh, because that dynamic data structure takes log n time to support that operation. I mean, maybe there is something in constant time, I am not sure, but even log n time is fine, right? That still gives us log square n time, right? Because just look at a non-tree tree edge here, what is happening? When it is being reported, popped out. It takes log n time. Then this also operation also takes log n time, right? So these two operations takes 2 log n time.
Just keep with each vertex the set of level I edges.
Mhm.
Just move them to level I minus 1.
No, how are we going to find them? What is this operation is asking you is just identify me a subset of the tree edges at layer I.
No, pick a vertex.
Hmm?
So all its vertices are partitioned across E1, E0, E1, E2 and so on.
All these vertices.
Pick a vertex,
Mhm.
all the edges incident on it,
Mhm.
they're partitioned into various levels.
Yes.
So now since this vertex is in this tree TU,
Mhm.
so I take this vertex and I look at all the edges which are of level I and incident on it, and then just move them to set I minus 1.
Yes, but you need to first find such a node that has a layer I tree edge incident on it. Because there might be many nodes in TU that do not have any.
So I know that U is there, and then I look at the neighbors of U, they're also there, right? At level I.
No, no. Don't you see this problem that okay, this is U, right?
Mhm.
And this is TU, okay? Say TU looks like this. Now this edge is I minus 1, I minus 1, this is I minus 2, this is I minus 2, and here you have a layer I edge. What this operation asks you to do is find this edge, and you cannot afford to probe through these edges. So the minimum you need is you need to report me this node directly, then I can afford to do something else. Okay, and that's why you will need that dynamic tree data structure with these labels.
The query the dynamic tree data structure allows us is find label and you have to give a vertex as a parameter, right? In find
Yeah.
label V.
So yes, find label V, it means look at the tree containing V.
Okay, so you okay, so whatever so you use this
Yes, look at the tree containing U, then find me a node which has a non-empty set of labels associated with it. Okay.
And it supports like 2 sets of labels. Like
Yes,
you need this.
yes. So I mean, you can just say that we are maintaining 2 dynamic tree data structures even, right? It doesn't matter. The forest is identical, the tree is identical, that is it. Okay, so assuming the dynamic tree data structure, are all the details reasonably clear? So our update time, amortized update time will be log square n, and the query time will be log n.
So you have this query which says find label V, right?
Hmm.
So what are the parameters to this query? Just the vertex V?
Yes.
And this only will find all, actually it will find just one vertex, right? Or
Yes.
which has a.
Yes. So if you just query that node, let's say find label U, it will say that okay, return you this node X. From this X, using your adjacency list the way you just said, you can quickly identify this edge. Then you will decrement this thing to I minus 1. And then you will just say that okay, destroy that label in the dynamic tree data structure.
So, I mean, no, the confusion is this, that you have Fi and you have Fi minus 1, right? And Fi, all the edges in Fi minus 1 are present in Fi.
No. What I said here.
So you have different, okay.
No, but Sam, I'm completely confused. So all I have is find level V. It will, I will give you a vertex V. It will give me if there is a vertex which has some particular level, and it will return me that particular
Yes.
vertex. Now you will be for every tree SE in TU with LE equal to I, you're going to do something, right? At this point of time. So at this point of time, whatever is all the tree S's in TU, I need to get them out
With the level I.
with the level
With the layer I.
With layer I,
right?
yes, yes,
Or,
yes.
So the thing is, so suppose when I ask, because I know this edge UV, so I can ask find level U and it will return a particular vertex to do this, right? Now, with the help of this, you're able to find some tree edge because you're maintaining.
Yes.
Because you're maintaining also probably adjacency list of this tree or whatever it is, and you're able to find this, right? Now, what should I do for the next?
Yes.
To find the next edge of this tree.
Yes. So, what you will do is, you have first found this edge in log n time, right, at layer I, okay.
Yeah.
Then what we will say is, you will just invoke a destroy label operation, just destroy this label from this tree.
Instead of destroying, aren't we just setting it to I minus 1?
That will go to the structure for I minus 1, na?
No, I mean, is it necessary to destroy the label? Because anyway, once you have found this label, we'll set it to I minus 1. So in the next query, we're again looking for an tree edge with I label.
What if that thing returns me the same edge?
No, but I've
So
already
it is
set.
changed to I minus 1 is what it's saying.
No,
Then you have to update the li.
you have to update this thing, right. The way I have described it, just look at this thing. The labels for Fi does not consist of the tree edges of layer I minus 1 or below. It just consists of the tree edges at layer I. Okay.
That still doesn't answer my question.
So, you will destroy, okay, first of all, you will just destroy that label, okay. Then you will again invoke find label,
Find level from
U. Then what will you will do? It will return you either a different edge, a new edge at layer I, or it will say that there is no such thing. Is that clear? So, this is basically a pseudocode, it is not even written that way. I mean, there will be a while loop, while do not you do not encounter failure with that find level thing, you just repeatedly invoke that query. Okay. Okay. So, you have 15 more minutes. Yes.
So when you're destroying a label, you're also adding that edge to Fi minus 1.
Yes, that will be taken care of in the next data structure, dynamic tree data structure for Fi minus 1. Then you will insert that as a label in Fi minus 1. But it's still just log n times O of log n operations.
So Sam, just to get her point also across, right? So it is all that find level can do is there a level or not? So whether it is I, non-I, doesn't matter because what I'm labeling with, it seems to me doesn't matter because otherwise she's right that I can just make it I minus 1 and that's no more.
Yes.
So it's like either there is a label or non-label and that operation we can support in order log in time so that every time all we are maintaining at this is that look, labels are only those people in the current forest which is, let's say ith label is only project, otherwise either there is an ith label or no label so that anything which it returns we know is of this particular type.
Yes, yes. Now alternatively, you can also support this decrement level operation and add a new operation called find min level. That also can be done. That will give you a different implementation. That is it. Okay.
We want to find max.
Min or max. Okay. Yes. Whatever.
What's the interpretation of the amortized time?
Mhm.
Is that if you do a large sequence of deletes, it's going to take
Mhm.
lots of it. But if you mix with inserts, then
No, insert is worst case log n
insert
time.
is anyway was
Okay. Okay. So, one other thing, I will spend probably 10 minutes defining this thing, just some organizational issue. Is it okay if we start this lecture at 11:15? Will anybody have any trouble coming here at 11:15 instead of at 11:30?
I don't have an issue because I have already fixed an appointment 9:30, 11:05, 11:10.
Oh, okay, okay. So that's fine.
I prefer if we start 11:30.
11:30. Okay, that.
Maybe if I read through what you have done before coming to lecture.
Okay, that is fine. The second question is then, the reason why I was asking is it okay if I be a little bit more flexible with the duration of the class? Say we start at 11:30 and we can finish any time in between 12:30 and 1:30. because I just don't want to leave something in the middle. So, I will, is that fine? I mean, if in the worst case we extend till 1:30 and on some classes we will just probably finish earlier as well.